Welcome to this explainer. Imagine, just for a second, that we're plugging a giant master cable directly into a planetary supercomputer. Seriously, we're going to run a full, high-tech diagnostic scan of planet Earth. We'll be looking at everything, from the absolute deepest history of the cosmos all the way to the real-time data flashing across our atmospheric and tectonic monitors right this very second. We've got a lot of ground to cover, and I promise you, the data readouts here are absolutely fascinating. Let's get into it.
To write a massive diagnostic like this, well, we need a foundational algorithm. Enter James Hutton in his principle of uniformitarianism. This was a massive historical shift, moving us away from early philosophical guesswork toward real modern empiricism. By stating that the present is the key to the past, Hutton established that the physical and chemical processes operating right outside your window today are the exact same ones that shaped the Earth billions of years ago.
Now, any reliable diagnostic scan requires some incredibly strict criteria, right? So we have to ground our analysis in fundamental, rigorously tested empirical definitions. I'm talking about the basic behavior of electrons or the exact nature of electromagnetic radiation. Think of these definitions as our literal source code. Without this standardized baseline, we honestly couldn't form reliable scientific hypotheses about massive, complex geological structures. The scientific method absolutely demands this kind of foundational clarity.
Section 1. Clocks in the rocks, measuring deep time.
Okay, let's dive right into this. For the longest time, geologists had to rely solely on relative dating. Thanks to Nicholas Steno's principle of superposition, we knew that in a stack of undisturbed rock, the bottom layer is the oldest. It's great for ordering events, sure, but it totally lacks numerical precision. So for our scientific theories to truly evolve, we needed absolute dating, a way to calculate highly specific numerical ages for these rocks.
The true game changer for absolute dating came when we discovered radioactivity and started looking closely at isotopes. So, what exactly is an isotope? It's basically an atom with the same number of protons as its siblings, but a different number of neutrons. And here's the kicker. Some of these isotopes are unstable, meaning they spontaneously decay over time into a completely different, stable element.
This brings us to a highly predictable, internal atomic clock that is literally ticking away inside the rocks right now. We call it the half-life. While the decay of any single atom is totally random, when you have trillions of them trapped inside a mineral crystal, they decay at a remarkably steady rate. This predictability is an absolute cornerstone for evaluating scientific reliability. The half-life is simply the precise amount of time it takes for exactly half of those unstable parent isotopes to decay into stable daughter isotopes.
Now, what's really interesting here is if you visualize this decay process like a digital HUD readout. When a mineral first forms from cooling magma, it locks in 100% parent isotopes, like uranium-238, for example, and 0 daughter isotopes. After one half-life, which for uranium-238 is a staggering 4.5 billion years, that ratio hits exactly 50-50. After 2 half-lives, it's 25-75. By measuring this exact chemical ratio with a mass spectrometer, we can calculate exactly how long that atomic clock has been ticking.
And this exact method actually solved a massive scientific mystery. Back in the 19th century, Lord Kelvin put forward a hypothesis estimating the Earth was only 98 million years old. But, you see, his model turned out to be scientifically unreliable because it completely lacked data on radioactivity and mantle convection inside the Earth. It wasn't until the 1950s that Claire Patterson applied brand new empirical data using mass spectrometry on ancient meteorites to upgrade our understanding from a flawed hypothesis to a robust scientific theory. We now know the Earth is 4.54 billion years old.
Section 2. Forging the Solar System, from the Big Bang to Earth.
Let's recalibrate the scanners and zoom out to the master timeline of our universe. 13.77 billion years ago, the universe rapidly expanded from a single point in the Big Bang. Fast forward a bit to 4.54 billion years ago, and our Earth forms. Now, the planet's very first chapter was the Hadean Eon, which was basically a chaotic, fiery hellscape of magma oceans and just constant asteroid impacts. But eventually, the Earth cooled, water pooled into our very first oceans, and by 3.5 billion years ago, we see the very first microscopic evidence of life.
But you might be wondering, how do we actually know about those earliest days of the universe? It sounds like science fiction, but we can physically look back in time. Astronomers can detect this ancient cosmic fog known as the cosmic microwave background. This is the literal, authentic afterglow from just 375,000 years after the Big Bang. Over billions of years, gravity pulled the slightly denser, hotter patches of this early energy soup together, and that eventually seeded the formation of every single star and galaxy we see today. Zooming in to our specific corner of the galaxy, the solar nebula model explains how we got here. A massive cloud of gas and dust collapsed in on itself. The material that was drawn to the center ignited and became our sun. Then, the leftover material flattened out into a spinning disk. Close to the intense heat of that newborn sun, only tough metals and silicate minerals could actually solidify, which is exactly why the inner planets, like Earth, are rocky. Further out in the disk, where temperatures were literally freezing, ice and gases accumulated to create the massive gas and ice giants.
Let's move to and see how this builds in Section 3, Monitoring Modern Earth, Real-Time Diagnostics.
To monitor the modern tectonic heat still trapped inside our planet, scientists use two very different diagnostic scales. First, we have the moment magnitude scale. This is a strict quantitative measurement of the pure physical energy released when a fault ruptures deep underground. Conversely, the modified Mercalli intensity scale is qualitative. It uses Roman numerals to measure the observed structural damage and what people actually felt shaking on the surface.
So, the crucial point here is that a massive release of underground energy doesn't automatically equal massive surface destruction. The severity of the shaking intensity is actually a complex equation. It depends on the earthquake's absolute magnitude, your distance from the epicenter, and critically, local soil and rock conditions. For instance, solid bedrock shakes way less than loose, watery sediment.
Section 4. Our climate footprint. System anomaly detected.
As we recalibrate our scanners to the modern atmosphere, the data points to a very specific and rapid anomaly. According to extensive peer-reviewed journals, 97% of climate scientists agree that currently observed climate warming is driven by human activities. And just to be clear on the reliability of this data, this consensus is heavily supported by leading global authorities, including the U.S. National Academy of Science and the IPCC. The core empirical data behind that scientific consensus is known as the Keeling curve. Charles Keeling started taking continuous atmospheric carbon dioxide measurements in Hawaii back in 1957, and the data shows an exponential increase. CO2 levels have spiked from 315 parts per million to over 420 parts per million today. To really put that into perspective, if we look at data trapped in 800,000-year-old ice cores, the natural historic maximums basically never exceeded 300 parts per million.
Because carbon dioxide acts as a greenhouse gas, trapping thermal radiation that would otherwise escape into space, it's significantly altering the planet's overall energy budget. As a result, we're currently tracking several concurrent, cascading impacts. We're seeing rapid global temperature rise, the thermal expansion of seawater, melting glaciers and ice sheets, and increased oceanic carbonic acid, which lowers the water's pH and directly threatens marine skeletal materials.
And this brilliantly illustrates how we use deductive reasoning to trace the exact source of this carbon. We do this by looking at isotopic fingerprints. The specific ratio of carbon-13 to carbon-12 in the atmosphere gives us a highly specific chemical signature. Because this signature perfectly matches ancient plant matter, which is what fossil fuels are, scientists can deduce with high reliability that this rapid increase isn't from a natural volcanic cycle, but explicitly comes from human extraction and combustion. The chemistry of the planet literally leaves a traceable footprint. Which brings us to the end of our planetary scan, and really to this final question. The Earth is 4.54 billion years old. It has survived massive asteroid impacts, global magma oceans, and deep ice ages. There's no doubt the planet will keep spinning, but humanity's role in this current, rapid anomaly is entirely unprecedented in the geological record. So I want to leave you with this to ponder. Based on the actions we are taking right now, today, what will our ultimate footprint look like in the planet's data logs a century from now? Thanks for joining me on this explainer, and as always, keep exploring.